us look at the exponential function 2 to the x. We know that x can be anything, but the answers can only be positive, so even not 0, because we have a horizontal asymptote of y equal to 0. And to get to the inverse function, we must swap x and y. So we get x is equal to 2 to the y. So if I have to solve for y, then I must take log both sides, and because I have a base of 2 there, I get log base 2 of x is equal to log base 2 of 2 to the y, and I know from my properties of logarithms this will be equal to y log base 2 of 2, which is equal to y. So I have a function y equal to log base 2 of x. So that means my inverse function is log base 2 of x, and this is now my inverse function. And we know that since the x and the y swap, if the y cannot be less than 0, then in this case the x can be only from 0 to infinity. And since the x can be any element of the real numbers, now the y can be any element of the real numbers. Again, because we swap the x and y, we get the mirror image in the line y equal to x. This new inverse function is called the logarithmic functions. You will encounter it a lot. The one that you most commonly encounter was log base 10, and on your calculator you just have log, and then we assume that the base is 10. First of all, on this graph, I've drawn the graph y equal to 2 to the x, and this is now y equal to log base 2 of x. We notice that this point, which is the point 0, 1, is now the point 1, 0 on the inverse function, and they are equidistant from the line y equal to x. If I take a point here, which is the point x equal to 2, y equal to 4, then the point x equal to 4, y equal to 2 will also be on the inverse. So the y here became the x here, and the x here becomes the y there. So the x and the y swap, and so it is true for each and every point on f of x, y equal to f of x. The x and y will swap to give us the logarithmic function here. Where the normal exponential function has a horizontal asymptote, now we have a vertical asymptote. X equal to 0, here we had the horizontal asymptote, y equal to 0, and this graph, the inverse graph, is always equidistant from the graph y equal to x. The function y equal to 2 to the x and the logarithmic function base 2, they are equidistant from this line y equal to x. The exponential function is growing very fast, but the logarithmic graph is growing slowly, but it still goes to infinity. You will encounter a lot of logarithmic functions in your first year mathematics, and especially where we deal with the natural log, which is ln of x, which is log the base of e of x, which is a funny number. E is approximately 2,7 something, and ln of x will lie in between log base 2 and log base 3 of x. But you will encounter that in first year mathematics. And also the function e to the x, which is slightly higher than the exponential growth, is slightly higher than this green graph, but it will also cut at y equal to 1. Let us look at the hyperbola. I've got here an hyperbola minus 1 over x plus 1. I want to mention first that if I take the simple hyperbola, just the one y equal to 1 over x, if I swap that, I will just get that x equal to 1 over y, so in this case that will also give me y equal to 1 over x. So the hyperbola is its own inverse. So that is not very interesting. So let us look at something more complex than just the mother graph y equal to 1 over x. So if I take this y equal to minus 1 over x plus 1, then I see that x can never be 0, so the 0 must be excluded from the domain of this function. And minus 1 over x can never be 0, so I can never have an answer of 1 for my y values. We know that just this minus 1 over x, y equal to minus 1 over x, lies in the second and the fourth quadrant. So it is this new graph, f of x is the simple y equal to minus 1 over x shifted 1 unit up. And this graph will have a horizontal asymptote at y equal to 1 because y cannot be 1, and it has a vertical asymptote at x equal to 0 because x cannot be 0. And it has lines of symmetry. We say minus x and plus x, but because we shifted it 1 up, we just add 1 to the lines of symmetry because the lines of symmetry shifts up with the graph. So if we swap x and y, then we get x is equal to minus 1 over y plus 1. So if I now solve for y, I must multiply by y both sides. Remember, y cannot be 0. So then I have xy is equal to minus 1 plus y. So then I take my y to the left hand side and I factorize. If I now divide with x minus 1, then I get y equal to minus 1 over x minus 1. Remember, the moment we swap our x and y, we also swap the properties for x and y. So in this case, y cannot be 0, and in this case, x cannot be 1. And in this case, x cannot be 1, and y cannot be 0. So here we have our inverse function, minus 1 over x minus 1. We see it's also a hyperbola, but in this case, it is y equal to minus 1 over x, shifted 1 unit to the right. We said that we swap the roles of x and y, so the domain and the range also swap. Okay, so here I said what I said there also. Although the hyperbola is a one-to-one function, it's a little bit more intricate to see the reflection. So what I did is I've drawn f of x and I've drawn the inverse function here. So that is my f of x. So it's minus 1 over x shifted 1 unit up, and you can see the line y equal to x is also now y equal to x plus 1. So this is y equal to x plus 1, and this line of symmetry is y equal to minus x plus 1 because plus x shifted 1 unit up and minus x shifted 1 unit up, and this is the graph y equal to minus 1 over x plus 1. If I look on the right hand side, then we see that this is the line y equal to x minus 1, and this is the line y equal to minus x plus 1, just as we have for this function here. And this is now the graph y equal to minus 1 over x minus 1. On this graph, I've now drawn both of them. So these are f of x, the green graph, and the red graph is the inverse function. And you can clearly see, and I'm going to use the blue here, this part here, and that part there are each other's reflections. And this part here and that part there are each other's reflection. And if you look at the distance here, from there to there is equidistant to there. And we also have our reflection about the line y equal to x, although we have other lines of symmetry. The reflection is again about the line y equal to x. It's not so easy to see it for the hyperbola. It's a little bit more intricate, but this reflection about the line y equal to x comes from the fact that we swapped x and y.